Well, thank you. First of all, I thank for organizer to invite me and to make possibility, opportunity to make talk about some very algebraic problem for specialists in differential geometry and physicists. Well, in my talk, I use vector for vector space of representation space of complex orthogonal Lie algebra SO and this representation called spin representation. It is irreducible in case n is odd, and the direct sum of two irreducible, each of dimension of 2 k minus 1, for n is equal to 2 k. And of course, I mean, in our case, irreducible component, and this irreducible I call this spin representation, and this representation integrate to representation of the group, and this is a two-sheet universal simply connected covering of, and this group has name spin, and this is the simple connected covering of group SON. Classification of spinor up to spin n. It has enough long history, and this history starts maybe bigger than 100 years with paper Cartan and with geometrical point of view, and Chevalier with algebraic point of view. But classification of full orbit start American mathematician Eguza in 1970, and he classified up to dimension 12. And after this, after Gatti, Miniberg, and really is Katz and Winberg, he classified case n equal 30. And Popov in same time, 1978, classified this in dimension 14. In dimension 16, this classification obtained two authors, Antonian and myself, in 1982. But in case n equal 15, is in this classification some gap, and we try to fill this gap. In all case before 15 and for 16, this representation is visible representation. This means that the null cone consists of finitely many orbits. And the first case when number of orbits in null conus is infinite is precisely n is equal 15. And for this reason, maybe I recall what is it null cone. Null cone is this is a set of common zero of all homogeneous invariant of positive degree, and we denoted this NGV, and all G orbit contain unique closed orbit, but in case null conus, element is in null conus if and only if the closure contain zero. Well, of course, main example in this situation is a joint representation of all reductive group in its Lie algebra, and the nil conus in this situation consists of nilpotent matrices or nilpotent element, and by analogy, in general case, element V belong in null conus, also called nilpotent. Well, first theorem in this direction is following. This theorem first, in some situation, proved Gilbert and in general Mumford. And the theorem is following: if element is nilpotent, but it's characterization of nilpotent element. In this case, it exists one-dimension torus such that closure of orbit of this point contain zero. And developing of this idea, Gilbert-Mumford criteria, it's possible to find among of all one-dimension torus satisfies these conditions that closure contains zero. To find some direction such that drag V to zero most quickly. For this is necessary to have some norm in representation space, and with help of this norm, it's possible to explain what does means this drag V to zero most quickly. In any case, for datum such that we fix with all nilpotent orbit is following. You find some element in Lie algebra H, semi-simple, such that HV is 2V, and H has smallest possible norm among all semi-simple elements with this property. And this H called characteristic of nilpotent element V. Following Hesselink, we defined, first of all, lambda V is all one-parametric subgroup of G such that corresponding one-dimension torus S contained in closure zero, all this one-parametric group with external property we denoted by lambda V, and with Hesselink defined following equivalence relation in nil conus. And the two element from nil conus is equivalent if lambda x is equal lambda g y for some g. This equivalence classes called the Hesselink strata, and for all representation of reductive group and null conus obtained with help this the definition of some finite partition of null conus. Yes, and in case, in main example, in a joint representation, each Hesselink stratum coincides with a single orbit. And in this case, this characteristic really defined and give definition of this in 1953, Evgeny Varechdinkin, when he classified conjugacy classes of SL2 subalgebra in Lie algebra G. And for representation, in some sense close to adjoint representation, strata also consist of a single orbit. In general, each stratum may consist of infinitely many orbits. And even if your representation is visible, I recall that this means that number of orbits in the null conus is finite. In this case, stratum may consist of several orbits, finite set, depending of, but this depends for choice of the norm. And there is some open question for NGV contain only finite G orbit. In this case, just a moment. In this case, it's possible to find some scalar product and some norm such that all stratum consist of single orbit. And after this, my colleague continued. Oh, please.
You see, we sort of split the theoretical part for such a computation part. Right. Well, I'm going to explain. There is an algorithm which is originating from Popov and which reduces all this stuff to the completely combinatorial data. So after that, if you are bored with it, you can take out the only information. Very soon there will be a publicly available package with which you can compute Hesselink strata, stratification of null cones, in cases comparable in size with the scheme representation, which is in this case has dimension 128. Things like that are available. They will be available. So you take this characteristic. This is a semi-simple element in your algebra, and it gives you a grading by its eigenvalues of the algebra and the representation. Then, I mean, this is just the definition of this grading. And so we also use this notation when you have grading from some point. So, in particular, for each h, G0h is a reductive subalgebra. It is the Levy subalgebra of this parabolic subalgebra. And this parabolic subalgebra acts on each graded pieces from some place up. And G0, this Levy subalgebra acts on each graded piece. So, in particular, H itself is in this G0, and we need this smaller subalgebra, which is orthogonal complement of the H itself in this G0. And then you have corresponding subgroups in G. Now, so why are these strata a good thing? Because they are geometrically very clear. I mean, unlike the orbits of which you have infinite families, and I don't think anybody knows for sure when you have infinite families of orbits, how do they behave. The strata, you have the finite amount of strata, and they are organized very well. So you take the corresponding parabolic subgroup, and so you take this associated bundle over the quotient of G by this parabolic subgroup. I think I'll skip at some point. So the closure of the stratum is covered by the total space of a vector bundle over G by P, of G by this parabolic group, and it's actually a resolution of singularities. I will explain it to you in a slightly different form. So, and more geometric approach was by several people, including Lyndon Ness mainly. So they used the gradient flow for the moment map in this case. So in this case, moment map can be described more explicitly. And so it goes from the projective space of the representation to the dual of the algebra of the maximal compact group as usual. And it has explicit description. And what happens is that gradient flow of this map, so under the gradient flow, all the potent elements tend to one of the singularities of the nil cone, and so accordingly the strata are just basins of attraction of the singular cones. So this is the geometric sense of this. This is all for the theoretical part. It's now finished. So now we come to the description of the algorithm of Popov, which is in his paper in 2003. And the basic thing there is that so you can find only a finite amount of elements in the fixed Cartan subalgebra, such that if you consider for each of the characteristics the certain open subsets of the subspaces consisting of elements of degree 2 and higher, then orbits of those, so I will give also this definition of this open subset later. These are basically representatives of strata. So each stratum actually, so if you, for each characteristic, if you take orbits of elements from this open subset, then you get exactly the strata. And they have purely combinatorial description. And in particular, dimension is very easy to compute. You take just dimension of the part of V2 and above and dimension of G below 0. And add them. This is dimension of the strata. And actually, there is a criterion when a semi-simple element can occur as a characteristic of some stratum. It just means that the corresponding second degree part is not completely null cone with respect to the action of this G0 to do. So then you have to compute this null cone of this particular thing, but it's smaller, and then you recursively go down to smaller and smaller. Right, so it only remains, all this combinatorial data have to be taken up to the Weyl group action, and the most computationally consuming thing is to find the Weyl orbits of this data together. So very roughly, I mean, if in the case of spin 7, what happens is that these green and blue things are root system B3 in this case, and the red ones are weights of the spin representation. So in general, you have a hypercube, and long roots are middles of the faces of codimension 2, and short roots are middles of faces of codimension 1, and then the weights are vertices of a smaller cube, hypercube of the same dimension. So in principle, I mean, from this combinatorial data, in particular for the spin representations, you could have some explicit formulas in principle. But what we did so far, we just had computations of the null cone in case of spin 15. That's what we did. So to summarize, you have such picture. So you have this vector bundle here, and so total space goes to the closure of the stratum, and the stratum itself is a union of those orbits which are not in the null cone when you project to V2, and it's resolution of singularity. So inverse image is just, I mean, inverse image is the same. So H is basically the smooth locus. And so, as I said, the definition is, so the projection to the second part must be time, so I will just very quickly maybe show you. Yeah, so there was a program before by Norbert Acampo, but we couldn't use it for spin 15. It worked for spin 16, but not 15. But with Willem de Graaf, he has now a package which already works. We checked it in some cases, or in particular in this case, and he's planning to incorporate it in GAP in the next version of his program SLA. And yeah, I think I'll skip mostly this text. I just want to show some samples of calculations. Yeah, there are some details, some technical details, but I think they are not so important. I just want to, so these are, for example, dimension of strata and dimensions of orbits of maximal dimension in the strata. So when the point is on the diagonal, it means that there is an open orbit in the stratum. So if it would be a joint representation of theta group more generally, then you would have open orbit in each stratum. But here, as you see, inevitably, you have many strata without open orbits, and for them you have this infinite families. So this is just a sample how we ensure that maximal orbit is indeed in V2 has this dimension and cannot have dimension higher, because you have grading, as I said before, of the group and of the vector space, and each vector from V2 shifts grading by 2, and we just ensure if it's maximal rank, then it cannot be. This is just one of the steps in the calculation. Then GAP gives you some particular representatives of orbits. Here, these are the usual weighted diagrams. I mean, these lines mean 120-degree angle between the weight vectors. This means 60 degrees. And what happens is that usually Sasha says this is all garbage, and then he uses his experience and expertise and comes up with good canonical forms for the importance, and this is the way it works.
Son, thank you very much for the interesting talk and this very civilized sharing of the lecture. Sometimes the quarters are shouting at each other. You're very civilized. So will you?
17? There are even more families of orbits, infinite families of orbits. I mean, we didn't try, maybe the graphs program gives you the strata again, but then you will have to work even more to find what are the maximal dimensional orbits in each of the stratum, and there might be several hundred or so. Here we have 169, and yeah, there is no theoretical obstacle. I mean, computationally it might be out of reach. We didn't try.
No, it's fair. So any further questions, comments?
You could use this for the image representation of a reductive group.
Sure. Yes, of course. Yeah. If dimension is not too high, I mean, if it's below 200.
But the idea is could apply.
Yeah, of course. Yeah. We just use. I mean, this is not the simplest case when you have infinite numbers of orbits, but it's sort of test bed for us.
Thanks.